Hello friends, in this video we are going to discuss about a numerical on ambipolar transport. In the numerical it is given that consider a infinitely large homogeneous n-type semiconductor with zero applied electric field. Assume that at time t equals to 0 an uniform concentration of excess carriers exist in the crystal. Assume the generation rate of the excess carriers, that is G dash, is 0 for t greater than 0, and consider that the concentration of the excess carrier is much smaller than the thermal equilibrium concentration, and calculate the excess carrier concentration as a function of time for t greater than equals to 0. In the given example, it is said that we have an n-type semiconductor, and in this n-type semiconductor it is given that the zero applied electric field, so we can say that the electric field applied is equals to 0. This is provided in the question, and it is also written there is a uniform concentration of the excess carriers. Since it has a uniform, so we can write that uniform concentration of excess carriers. Since there is a uniform concentration of excess carriers, so we can say that here that is the diffusion motion of excess carriers will be equals to 0. There will be no diffusion motion of excess carriers. Another thing is given that the generation rate of the excess electrons on the excess carrier G dash is equals to 0. So we can write that G dash is equals to 0. These are the things that is given in the question, and it is also given that the concentration of the excess carriers is much smaller than the thermal equilibrium electron concentration, that is the concentration of the excess carriers, that is the del P. This is the concentration of the excess minority carrier holes in the n-type semiconductor is much less than the thermal equilibrium electron concentration, that is N0, and it means that low level, it signifies that this is a low level injection. So low level injection condition is given here. So from this, if we modify the transport equation, then we can write that the ambipolar transport equation for this n-type semiconductor will be like this. We know that is dp del 2 del p by del x square minus mu p into e that has been applied to del of del p del x plus g dash minus del p divided by tau p0 is equals to del of del p by del t. So this is the equation of the ambipolar transport equation in an n-type semiconductor. and it has been given that the E applied is 0. So we can write the second term, this second term of the equation will be equals to 0 because E is 0 here. Another one, G dash is 0. So this term is also equals to 0. And since there is a uniform concentration of excess carriers, so diffusion motion of the excess carriers will be 0. So the first term containing the diffusion motion of the carriers, this will also be equals to 0. So the final equation that comes out of this ambipolar transport equation will look like that del of del P by del T is equals to minus del P divided by tau P0. So this is the final equation that can be written from the ambipolar transport equation after putting all the conditions. So we have modified the ambipolar transport equation using the situations that is given in the above equation. So according to this question, the low level injection is present. Since the low level injection is present, we can write since low level injection is present, so we can write that the minority carrier lifetime, that is, we have considered a n-type semiconductor, so the minority carrier lifetime will be the carrier lifetime of the holes, that is tau p0 is constant. So from this equation we can write that d dt is of del p will be equals to minus del p divided by tau p0. So if we solute this equation, after soluting this equation, this is a first order differential equation. So if we solute this first order differential equation, then we can find the value of del p. So the value of del p with respect to time will be equals to del p of 0 e to the power minus t divided by tau p0. Hence, this will be the value of the excess hole concentration with respect to time. And del p0, this del p0 is the concentration of excess carrier. So I can write it as concentration. This del p0 is the concentration of the excess carriers or the excess holes that exist at t equals to 0. So now if I want to draw, so from this equation, if we want to draw the del pt, del of pt with respect to time, that is del of pt, it will look like this will decrease exponentially, and at this point the t value is 0. So at this point the del p value will be del p0. It will decrease exponentially. So the concentration of the excess hole decays. So we can say that the excess concentration of holes decays exponentially with a time constant, and this time constant will be equals to the minority minority carrier lifetime. This is the minority carrier lifetime tau p0. So from this equation, we can see that the time constant of the exponential decay will be equals to the minority carrier of the lifetime. So according to the charge neutrality condition, we can say this, that del p t, we have found that del pt was del p0 e to the power minus t divided by tau p0. So this was the excess hole concentration changing with time, changing with time. But if we apply the charge neutrality condition, then we can write that del P is equals to del N, that is the excess carrier of the hole should be equals to the excess carrier of the electron. So from this we can write that del NT will be equals to del P0 e to the power minus T by tau P0. There will be the same equation for the excess electron concentration. So in this way we can find the excess carrier concentration as a function of time. Thank you.